So let me write down the proof. So the proof, so as I have told you, it is going to be by contradiction. So we assume what? We assume that, so I'm going to prove this general result, n squared plus 1 implies either increasing or decreasing. Okay, n plus 1. Assume that we can find what? We can find some sequence so assume that we can find some sequence of length n squared plus 1 such that what? Such that there is no increasing or decreasing subsequence of n plus 1. Such that there is no, so we cannot find any increasing subsequence of n plus 1 nor any decreasing subsequence of n plus 1. Is that okay? So this implies what? So yeah, this implies what? This implies what? Any subsequence, okay, or any increasing or decreasing subsequence any of them, this implies any increasing or decreasing subsequence must have length what? Any increasing or decreasing. It cannot be, you cannot find n plus 1 long. So what can be the length of an increasing subsequence? You cannot find n plus 1, so what can it be? It cannot be n plus 1. It cannot be n plus 2. Can it be n? Yes. Can it be n minus 1? Yes. Okay, so must have length between too long. Have length. So let me write down less than or equal to n. Is that okay? But you know that it is of length 1, 2, 3 up to n. Is that okay? Is that okay? Now, okay. Now, so now we do what? You take a look at the original sequence. At the original sequence, and look at and in particular look at the ith number, ith leftmost number. Okay, so what is meant by this? So let me use so you have the numbers. So let's give the numbers names. So let's call the numbers, the first number, let's call it S1. Is that okay? I don't know what is the value of S1, but let's call this S1. The next number, let's call it S2, and then S3, and then so on and so forth. How many numbers are there? So there are n squared plus 1 numbers. So these are all the numbers. Is that okay? Is that okay? So we are looking at the ith leftmost number. So what is the ith leftmost number? The ith leftmost number is this number Si. So after Si, it is Si plus 1, the number after this, and so on and so forth. So in the end, this is Sn squared plus 1. Is that okay? So these are the numbers that we have. So for instance, the first number in the example is 5, the next number is 3, and then 7, and then 2, and then 1. Is that okay? So this is how I call them. So because I don't want to call it equal to 5, I don't want to call it equal to 3 because it is just one example. Here, I call the first number, give it a name. I call it S1. the first number in the sequence S. So let's call this sequence S. Okay, so this is the sequence S that we have. Okay, so let's fix this number. And then what we are going to look at? We are going to look at if we include this number, include this number to what? If we include this number starting from this number, if we start exactly from this number, what is the longest increasing subsequence that you can find looking towards the end? And what is the longest decreasing subsequence that you can find if you look it towards the end? Is that okay? So for each number, let's call this one. I'm going to use that example soon. But we are going to find two things. So first of all, find the length of the longest increasing subsequence that begins with this number. And also, we also want to find out what is the length of the longest decreasing. Don't worry, this is really complicated. So we are going to define some complicated thing that begins with also SI. Okay, difficult to understand. Look at this example. Okay, if you look at this example, okay, for this number 1, let's take a look at this number 1. If we begin, so we are going to look at it up to the end. For this one, we want to find out two numbers. The first one is the length of the longest increasing. So if we include this one, what is the length of the longest increasing that you can find? So for instance, you have 110. So this is an increasing subsequence that begins with 1, and the length is 2. Is that okay? You can have 168. This is another increasing subsequence that begins with 1, and this time the length is 3. Is that okay? Is that okay? And then can we find out a longer increasing subsequence that begins with 1? Is there anyone? Is there any? In this example. So 168 is an increasing subsequence of length 3. Can I find a length 4? Can I find a length 4? 1468. Very good. 1468. So there is a length 4 increasing subsequence. Is that okay? And how about length 5? Are there any length 5 increasing subsequence that begins with 1? No, there is no. So the longest increasing. So for this one, we get the longest increasing has length 4. Is that okay? The length is 4 numbers. How about the longest decreasing? So the longest decreasing subsequence that begins with 1. You have to include this one. So what can it be? What is the length? 1. The length is 1. 1. 1 itself is 1. Okay? And then it is already the smallest number. You cannot include any other number. So the longest decreasing is 1. Is that okay? So for 1, we get these two numbers. Okay? Let's do another one. This time let's fix 7. Okay, for this 7. So for this 7, you are going to look at starting from 7 up to the end. Okay? And we also want to get two numbers. Okay, for this 7, what is the longest increasing? What is the length of this longest increasing? I can see 710 or 79. Am I correct? And then I can also see 78. But you cannot get 3. The longest increasing subsequence that begins with 7, the length has to be 2. Is that okay? If you're okay with this so far, could you please raise your hand? Okay, very good. This is important. Okay, very important. We need to understand this. So, yeah. So let us spend more time to make everyone else understand here. And this time, let's also investigate what is the longest decreasing that begins with 7. So I can see 7, 2, 1. So this is of length 3. I can see 7, 9, no. 7, 6. But this time this is only of length 2. Is that okay? So the longest decreasing that begins with 7, you include this. The length is 3. Is that okay? The length is 3. Let's do one more example. So let's do which one? Let's do 10. How about 10? Okay. Let's use the white chalk. Okay, so let's begin with this 10. Okay, let's start with this 10. So from 10, we look at everything until the end. And then we also want to find out what is the longest increasing. What is the longest increasing? The longest increasing is going to be 1, because 10 is the largest number, so you cannot make it longer. Okay, longest increasing, that begins with 10. You have to include this 10. And you have also the longest decreasing. Longest decreasing, then this time it is 3. Is that okay? 3. Is that okay? So everyone understands the definition. Am I correct? So each position, for each number at any position, we can define 2 terms. One is the length of the longest increasing, and the other is the length of the longest decreasing. Is that okay? Okay. Okay, let us continue the proof. So we define this, and then we continue the proof. Now let's take a look at the ith leftmost number and define these 2 terms. We find these 2 terms. And then what? Okay. So each of the length each of the 2 lengths, each of the lengths must be between 1 and n. Yeah, because there is no increasing subsequence of length n plus 1. There is no decreasing subsequence of length n plus 1. So all the lengths, these are the lengths about the subsequence, right? All the lengths has to be between 1 and n. Okay? Now this is the first thing that we have. Okay. But then, this is the other thing. So we will hope to get a contradiction. But what we can find, but for different position I and j. So if we look at 2 different positions, I and j, look at the numbers si, sj, starting then the 2 numbers, the 2 lengths cannot, so this is an observation we are going to prove, cannot be both the same. And this is the key thing that we have. So we are claiming that, so you look at this. So this one says 1, 3. This one says 2, 3. This one says 4, 1. Is that okay? Now I'm claiming that, okay, the 2 numbers, I'm not saying that this number is not equal to this number. So I'm not talking about this. I'm saying that if someone has longest 1, longest increasing 1, longest decreasing 3, then you cannot find another one that has longest increasing 1 and longest decreasing 3 at the same time. Is that okay? So what I'm claiming is that for any 2 different positions, let's say this one and this one, they cannot have this number and this number to be the same. Is that okay? So this one is 1, 3. This one is 4, 1. Let me do another one. So for instance, this one, so for this 9 is going to be having the longest increasing is 1. The longest decreasing is 2. Is that okay? So these 2 have the same here, 1, 1. But then the other part has to be different. Is that okay? And similarly, let's do another one. Let's see longest increasing 2, longest decreasing 3. So for instance, let's look at this 3. The longest increasing will be what? 3, 9, no, 3, 7, 9, no, 3, 4, 6, 8. So the longest increasing will be 4, and the longest decreasing will be 3 to 1 of length 3. Is that okay? Now if you compare this 3 and this 7, they have the same longest decreasing, right? But in that case, they don't have the same longest increasing. Okay? Okay? I'm claiming that they can have the same part for one thing, but the other part has to be different. If this is 2, 3, then no one else can be 2, 3. This is 1, 3, no one else can be 1, 3. This one is 1, 2, no one else can be 1, 2. This one is 4, 1, no one else can be 4, 1. What is the reason? Okay. What is the reason? Look at it. So let's say this is the number Si, and let's say this is another number Sj. So let's say J is somewhere after Si. Okay? Now, let's say this is X and then Y. Let's say this one is X prime and then Y prime. So let's say this one has the longest increasing X and then the longest decreasing Y. This one has the longest increasing X prime and the longest decreasing Y prime. Now, look at these two numbers. They are distinct. They are not the same. So if Si is greater than Sj, let's say if Si is greater than Sj, then Y has to be greater than Y prime. Does that make sense? If this one is larger, this one is smaller, then the longest decreasing starting from Si has to be longer than the longest decreasing starting at this position. Is that okay? Similarly, if this one is smaller, this one is larger, then what will happen? Then X has to be longer than X prime. Is that okay? Is that okay? The key point is that for any longest increasing sequence that we define, we include this number. We include this number. So if this number is smaller, then we can have this number and then get this number and continue to get the increasing. So we get a longer increasing. So if this one is smaller and this one is larger, then the increasing parts cannot be the same. On the other hand, if this one is large, this one is small, then the decreasing parts cannot be the same. So none of them can have the same increasing and same decreasing length. Is that okay? Is that okay? Okay? Key. This is the key observation. Okay? Okay. Then we get a contradiction. Wow. Where is it? Where is the contradiction? Where is pigeonhole principle? Yeah, where is it? I'm skipping a little bit of things. Where is it? So let me give you a hint. Okay, so look at it. Every length has to be between 1 to n. Is that okay? So how many variations are there? This can be 1 up to n. Am I correct? This can be 1 up to n. So how many different types of lengths that we can have? You can have 1, 1, 1, 2, 1, 3 up to 1n, and then 2, 1, 2, 2, 2, 3 up to 2n, and n1, n2, n3 up to nn. Am I correct? As these two parts. Is that okay? So how many different kinds of lengths that we can have for each position? Yeah? 2n? More than 2n. How many different? N square. N square. So the n choice for, yeah, I'm skipping a little bit of things because we are going to talk about combinatorics soon. Yeah, I'm asking you to think ahead. Okay, so there are n variations of longest increasing length. There are n variations of longest decreasing length. Is that okay? So there are n square different types of lengths that you can have. Okay, you can start from 1, 1, and then you can have also 1, 2, you can have 1, 3 type, and up to n type. Is that okay? So there are only n square different types. Okay? N square different types. But how many numbers do we have? How many? We have S1, S2, S3, up to Sn squared plus 1, right? So there are n squared plus 1 different, so there are n squared plus 1 positions. Each position, we need to choose a type. There are how many types? n square types. What do we have? N square plus 1 position. Each position has to choose one type, and there are n square types. So what does it mean? What does it mean? Two numbers, two positions must have the same type. Is that okay? N square plus 1 positions. Each position has to choose a type. There are n square different types. Okay, n square plus 1 position, n square types. Pigeonhole principle says 2 or more must have the same type. Okay, then we get a contradiction. Where is the contradiction? Here. Different positions must have different types. This is what we have claimed. And suddenly, by pigeonhole principle, we will find that there exists some two positions have the same type. Then these two are contradicting each other. So together, they get always false. So we get a contradiction. So if we get a contradiction, what does it mean? It means that the original assumption has to be wrong. Yeah, because we are showing some statement implies some contradiction F. So it must mean that the negation of the original statement is true, or the original statement that you have an assumption there has to be wrong. So this completes the proof. Is that okay? So we assume something wrong, and then as expected, we get a contradiction. This is what we hope. Because once we get a contradiction, we know that what we assume at the beginning is wrong. You can only assume a wrong thing to get a contradiction. We cannot assume a true thing to get a contradiction because it is against logic. Okay? So in that sense, we have proven this theorem. Okay? Very, very complicated, right? Yeah, so let me review. Okay, so this proof is complicated because two things. One is, okay, so or maybe you can think about there are three things. So for the first one is we are using proof by contradiction, and this is some technique that is new to you. The second thing is that we have to define something. You need some creativity here to define something that you don't know. You don't know why you want to define this. Okay, you are defining things out of nowhere. But this definition of things helps you to connect to the pigeonhole principle. So this is the third part, that you apply the pigeonhole principle to help you to get the contradiction. Okay, so that's why this is a very, very complicated proof. And even if you have idea that you are going to use proof by contradiction, how to get the contradiction is also not trivial. So you have to make this observation. Different positions, so this is the observation that you have. The different positions, you need to have different types. Okay, this is not trivial at the beginning, right? But once you get this, different position has to have different types. And there are just too many positions that we have. There are n squared plus 1 positions that we have. And there are not enough types. So in that sense, we get a contradiction. Is that okay? Okay? Yes. So I hope you like this. Okay. So let's take a 10-minute break first, and then after we come back, let's talk one more simple example. Okay. Okay.